Hello and welcome back to Introductory Electromancy. In this episode, we are continuing to work on our transcranial direct current stimulation device, which you, dear viewer, can use to enhance your own mind. Different placements of the electrodes on your brain will enable you to alter the way in which your brain functions. I'm particularly fond of this one. And yeah, I'm following my own instructions, which I published in 2013. With this device, you too can assemble your own collective of superhuman cyborgs and save the world. Do not use it on anyone without their consent. Make sure that people who use it are over the age of majority in your jurisdiction, and anyone with a history of seizures or metal plates in their head should not use this. Otherwise, it is pretty safe. To the best of my knowledge and understanding, I am not a doctor. I am but a random human who builds mind control devices for the internet. Now, in the previous two episodes, we analyzed the circuit. We talked about transistors. We talked about resistors in series, how they just add up. So let's get to practical breadboarding. After all, the point of all this math and theory is so that you can apply it in the real world. The real world which we inhabit together. Oh, what a joyful place it is. What fun, what joy. Many world. Wow. So, this is a pretty simple circuit. And I am lucky enough to have all of the parts on hand for it. 12 kilo ohm resistor. Let's see if there's some way I can let you see the schematic at the same time. I know this filming setup is not optimal. I'll get an optimal setup someday. Today is not that day. This is just the best I can do with what I have on hand. I wish that I had done more with my time in existence, but I mean, it's not over or anything. I always feel like I could have been a bit more efficient, more productive, spent less time dilly-dallying, enjoying myself, what have you. I don't know how we're going to fix all of this, dear viewer. I have some ideas which I will share over time, but this is a big one. A machine that could make you smarter or happier, let you make other people smarter or happier. So here we have our 12 kilo ohm resistor and our power indicator LED. I'm not including the switch in the breadboarded version of the schematic. I'll directly connect it, so it is as if the switch is always closed. So we have our 12 kilo ohm resistor, we have a green power indicator LED. You could use any color you want. Then we have another 12 kilo ohm resistor. Going from the red line here, which is the positive rail. Note that the LED is connected back to the blue rail, negative rail, and then these little groups of 5 are all connected horizontally. So current can flow here to this connection, then back through the LED and the resistor, with the resistor limiting the current through the LED. So now we have our second 12 kilo ohm resistor, then 3 diodes in series. All are 1N4004. To the best of my knowledge, 1N400 whatever will work for this. They make 1N4001 through 1N4007. The different numbers indicate that they can block various reverse voltages. This circuit uses them because they have a reliable forward voltage drop, so the reverse voltage doesn't even matter. You can see the little colored band on the diode, if I can focus on it, is on this side. Current flows from plus through this resistor, then through this diode, then it'll flow through 2 more diodes. Conventional current, which flows from plus to minus, is what I'm using in these descriptions. Could I use electron flow? Yes. But then the little arrow on the diode wouldn't be pointed the way the current flows. And that would just make me sad, dear viewer. So, current flows this way. I wonder if more light would help. No, that helps more. Current flows through this resistor, then through this diode, then through this diode, and then through another diode back to the ground rail, which is the blue vertical line on my breadboard. And then we're going to want to have access to the voltage at the top of these 3 diodes, because that gets fed into the base of a transistor. One of the nicest things about electricity is that the physical layout of the wiring, at least for low current circuits that are not operating at high frequency, the physical layout and shape of the wiring, it doesn't really matter until you get to high frequency, and then it starts really mattering. Or high voltage, and then whether or not the surface is smooth controls whether or not you get corona discharge coming out of it. Anyway, it's nice. You can move apart wherever you want, and just extend the wires to it, and it'll all continue to just work. I'm going to try using a lamp. It does seem to help. So our transistor is a TIP31C, TIP31C, which is barely legible. I might actually use Zoom for this. Wow. Behold, the TIP31C. All its majesty. I have pulled up the data sheet for that transistor, and the thing we want is the pinout. This thing. Pin 1, this is a top view of it, with the tab on the back, so it's like so. Pin 1, which is the one on the far left here, is the base. Pin 2 is the collector. Pin 3 is the emitter. So the base on our schematic is here. We want it connected to the top of these 3 diodes. You can see, lo and behold, it is. Now the emitter is going to be going through a 100 ohm resistor, then a 560 ohm resistor, then to ground, which will be the blue vertical line on our breadboard. And it doesn't actually matter which order you put these in, because they're in series, the values will add. They're equivalent to a 660 ohm resistor, but that's not a standard value. These two are common and easy to find standard values. And it doesn't matter which way you point the resistor. Unlike the diode, a resistor acts exactly the same in both directions. This is the 100 ohm resistor. So that goes, oh, I take that back. That's the 560. See, I'm already reversing my own schematic, but I'll try to follow it to the T, dear viewer. I'm not sure how used to all of this you are. 560, green, blue, brown, gold. 100 is brown, black, brown, gold. The gold means plus or minus 5%. So the resistor could be 5% bigger or 5% smaller in terms of resistance value. Because this is the real world and we can't actually build anything ideal here, which is very sad, so everything is specified as for how not ideal it's allowed to be. Okay, and then two more resistors, the 2.2 kilo ohm resistors. 2.2 kilo ohms is just red, 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 gold for the color bands. Those go here. These are the safety resistors. They make it so that even if this transistor fails short circuit, you will not get a dangerous amount of current flowing through your head. I haven't had one of these devices fail, and I've built and shipped a couple dozen of them, but it's much better to be safe than sorry. You only get one brain, dear viewer. Only one, until you can build your own external one, connect it to yours, and then gradually transfer your consciousness to it, which I hope you'll be able to do pretty soon. I would recommend using a neuromorphic architecture that is analog and continuous in the time domain. I think that having a continuous processor is an important part of why our consciousness behaves the way it does. But I have no evidence for this, so you could simply ignore my claim, dear viewer, if you so desired. But having nonlinear feedback and a connection to random processes enables your brain to not necessarily behave the exact same way, even if you put it in the same situation multiple times. The non-deterministic jostling of the little atoms at your membranes and synapses, combined with the way that your brain amplifies small signals, feeds them back in a nonlinear fashion, means that tiny changes at the membrane themselves can result in large overall changes in the way that your brain is operating, which connects you to the basic fuzz and jiggliness of the universe, which is then partially manifested through the way in which your brain operates. But that's kind of beyond the scope of this video. This side of the breadboard we'll get to eventually someday. I haven't decided if I want to try and teach you digital logic and basic computer architecture and processor design before we learn how to use microcontrollers like the Arduino Nano, or exactly how all of that's going to be structured. This seemed like the best first practical project because when you build your transcranial direct current stimulation device, you can then use it in order to boost your ability to memorize and learn, which should help you learn the rest of all of this information about electronics more rapidly and more efficiently. At least that is the hope. But Neither here nor there. Neither here nor there. I am going to link to tDCS placements. You should know that all of their on-site links are broken, but the pages are still up. So /placement/ and then what is the link? This is what I get for referring you to resources that are more than a decade old. /placement/ interesting. So then, why? I do not understand how and why this website is broken, because it really looks like all of the things are here. Anyway, I am following my own instructions to build this device. It's a happy, fun time. We've already analyzed the circuit. Now we've built it. Now it's time to power this baby on. So I have a lab power supply. You don't need one to test this circuit. It's more for demonstration purposes, so that I can adjust the power supply voltage and we can see how the circuit acts. This circuit is powered by 4 9-volt batteries as designed. This is a different design of the same circuit. Well, it's not the same circuit. It's a different design of the same device. If you want this design, it's on my GitHub. It's called SMD tDCS because it uses surface mount devices instead of through-hole devices. But these through-hole devices are easier for you, who I'm assuming is a beginner, to work with. So this is the version that I'm putting up with these instructions. So we connect our positive and negative leads. Step 1. All right, so the power LED turns on. Now, as a general example for how one designs circuits, you get your schematic, either off the internet or one that you've designed yourself. You do math in order to figure out whether or not everything is running in the safe operating region. Then you build it on a breadboard and poke. As long as you're not using metal oxide semiconductor devices or anything static sensitive, you poke it and make sure that none of these things are too hot to touch. If it is too hot to touch, it is probably not running in a safe power dissipation, at a safe power dissipation. The actual maximum voltage or maximum power for maximum temperature for a semiconductor is about 100 Celsius, around the boiling point of water, 212 Fahrenheit. So too hot to touch comfortably is actually lower than that. So if you make sure that none of your parts are too hot to touch comfortably, you'll actually be allowing some safety margin up to the absolute maximum temperature of operation of semiconductors. 100 Celsius is just the most common value for silicon semiconductor devices. Let's see, this tip 31C maximum ratings. Okay, that's, wow. This one claims it can go up to 150 Celsius. I wouldn't recommend actually running things that hot in practice. Lower is better. Running things at a smaller percentage of their rated power is better. So we have our circuit. Our circuit is built. The little power indicator LED is on. There should be a 2 milliamp current running from here to here if we test it. This is actually lower than the voltage it'll get from the batteries. 36 volts is the nominal voltage it would be getting from the batteries. So To measure this, we set this to the 20 milliamp range. And then we should get a reading of about 2 milliamps. And we are not. And why is that? It is because I have wired the circuit wrong. This part corresponds to this resistor, but this resistor is not supposed to be connected to ground at one end. It's supposed to be connected to the positive supply rail. Now we are measuring 1.9 milliamps, which is not quite the 2 milliamps that we want. However, we're also not powering this thing with its full rated voltage. So, odds are, if we actually did, we'd get the correct output voltage. So, stacking voltage sources in series makes them add. Putting them in parallel increases their current capacity. Now, this battery has a voltage of 9.45 volts. Since it is brand new, it is actually bigger than 9 volts in terms of output voltage. If you're wanting to calculate the safe operating area of a circuit running off a 9 volt battery, assume a maximum voltage of 10 volts, just to be on the safe side. But if we put that in series with this, and we want its output voltage to make it so that the circuit is receiving 36 volts, then we need this to be at about 27, 26.3 or 0.6 for exactly 9.4 volts. So 26.35 or 0.55. This is being ridiculously over precise, but that's all right. So to put things in series for batteries, you'd go plus to minus, plus to minus, plus to minus, and then you'll be left with a plus and a minus on the outside, which function as the overall positive or negative terminal of the compound battery you've constructed. So now, with the actual rated supply voltage, what do we get for an output current? .93, 1.94. All right. So this particular circuit is coming up on the low end of what I would expect. In the past, this circuit has usually been pretty good about being almost exactly 2 milliamps, and 1.94 milliamps is pretty close. And all these parts are rated to an accuracy of plus or minus 5%, but it will bug me a little. I guess I happen to get particularly large resistors for these two values, which would tend to decrease the output current. Could slightly alter these resistors' values in order to change the operation of the circuit, but I don't know if it's necessary in this case. Just for funsies, may as well. You never have too many resistors, do you? Here's a 1 kilo ohm resistor. Putting resistors in parallel decreases their resistance. So if you have two identical resistors in parallel, side by side, they act as if it's one resistor with half the value. Whereas if you put them in series, they'd act like they had double the value. Now, these resistors don't match. This is a 1 kilo ohm resistor that I'm going to put in parallel with this 100 ohm resistor. And resistors in parallel do not simply add. If you have some resistor and another, I'm drawing them in series. If you have some resistor in parallel with another resistor, and this one is RA, and this one is RB, and you want to convert them to a total equivalent resistance, REQ, then REQ equals 1 over RA plus 1 over RB. I believe this is called the harmonic mean. And this description of it is if you wanted to keep adding resistors in parallel and get the total overall value, you can just keep tacking terms onto the bottom here. For just two resistors, there's a special case where it's RA times RB over RA plus RB, which is an algebraic rearrangement of this equation here. But this is the general form, and in my mind, it's easier to remember. So this lets us change the value. If I want to put a 100 ohm resistor in parallel with a 1000 ohm resistor, then the overall resistance will be $90.9 ohms. So it's equivalent to slightly decreasing this resistor. I think when I built a bunch of these, they ranged between, it was like 1.9 milliamps and 2.02 milliamps. And so I made sure the design erred on the side of having slightly less current because the University of Göttingen tDCS safety protocols recommended not having more than 2 milliamps. Trying not to melt anyone's brain with the instructions I have put out into the world. That would be bad. Frowned upon. Not supposed to melt people's brains. In any case, now we have added another resistor in parallel, and we can measure the output current. Now it is 1.96 milliamps, which is close enough to 2.00. The other thing to note is that changing the supply voltage doesn't actually change the output current all that much. This circuit is a current regulator, so it'll maintain a constant output current across a wide range of supply voltages, and that's important because transcranial direct current stimulation relies on a constant output current. So we added a 1 kilo ohm resistor there in the circuit, measured the output voltage. So if I increase this, the value of the current should be very similar. Ooh, all the way up to 1.99. All right. And then we turn it way down. 1.87. So we're looking at about 10% variation over that range of voltages.